So I have to start from the definition once again. So the definition that I was writing is as follows. Just carefully observe. The things are not that easy, and you have to understand the words written in each definition. So first of all, I'm writing the definition. A subset S of a vector space. A subset S of a vector space V is called, and I'm writing linearly dependent. Don't think that I'm making a mistake. I'm writing it intentionally. Linearly dependent if there exists a finite number of distinct vectors u1 u2 ... un in capital S. Remember, this term is important. Distinct. And scalars a1 a2 ... an. Now what I'm writing is very important. Not all zero. I will explain this particular part. such that a1 u1 plus a2 u2 plus ... plus an un is equal to 0. In this case, the vectors u1 u2 ... un are also linearly dependent. Okay. If a set of vectors are not linearly dependent, then these vectors are linearly independent. In other words, a1 u1 plus a2 u2 plus ... plus an un is equal to 0 will always imply a1 is equal to 0, a2 is equal to 0, ... an is equal to 0. This definition is actually very important definition, and try to read the definition very carefully for to save time. Henceforth, I will consider linearly dependent as LD in short, and linearly independent, I will consider this term as LI. So we'll consider this as LD and this will consider LI. Now what it is saying. Now forget about the example that I was discussing in my previous session. Let's talk about what we know, what we are comfortable with. Let's talk about numbers. Now you see that if I give you two numbers, for instance, x and so it's the same equation, if I consider that x plus y equal to 0, then you know that the solution of the equation is x equal to minus y, or in other words, you can say that y equal to minus x. Okay, so what do we get from this equation? Solution of this equation, we are getting that if I take the vector x and if I consider the vector minus x, and if I add them together, we get the 0 vector. Just think like this. But you see that this in turn implies that we can represent always x, we can represent always as 1 into x, and minus x can always be represented as minus 1 into x, whose sum is 0. But these scalars 1 and minus 1, they are not 0. They are not equal to 0. Okay, so these vectors x and y, they are not linearly independent. They are linearly dependent vector because y is dependent on x. And therefore we call this is the definition of independent variable and dependent variable. That's why we call x as independent and y as dependent. Because their linear combination is 0, but their scalars are not 0. But in the example that I was choosing, that example that I chose, where I considered the vector 1, 0, and we multiplied this by a1, and we considered the vector 0, 1, we multiplied that by a2. And we, instead of writing 0, because it is a number 0, we considered the similar thing with 0 vector, because 0 vector is the 0, 0, 0 is the 0 vector of R2 space. So we chose this, and after calculation, we found that this thing can only happen. The only possibility is that the individual scalars are 0. A1 equal to 0 and A2 equal to 0. And therefore, these vectors 1, 0 and 0, 1, they are not LD, and hence they are LI. Hence they are LI vectors, linearly independent vectors.
Sir, please explain this on 1 second.
Which one? Which part?
This one 1, 0, 0, 1 are not LD. Thus they are LI. This line.
Have you understood? Be with me. Have you understood the definition of LD and LI? Have you understood the definition? First of all, make sure that you have understood the definition.
Not clear, sir.
Not clear.
Yes, sir, not clear.
Not clear.
Okay. Just a minute. Let me see, so with some other examples, whether I can, can I get any other example by which I can make it? Okay, for example, suppose I'm giving you a set, capital S, and you are going to be remain unmuted. Any of you are going to tell me this particular, they're going to give me the answer to this particular problem. I am giving you a set 1, -3, -2, 4, and this is the matrix, which is the first element of set capital S. And I'm giving you another set -2, 6, and 4, -8. This is another element of the set. So the set has 2 elements only. It's a finite set. If I now ask you that whether this 1, -3, -2, and 4, this is one, I can consider this to be a vector, because it is, matrices are always considered to be vectors. And V2 is -2, 6, 4, -8. I want you to tell me whether these 2 vectors are LI, linearly independent vectors, or linearly dependent vectors. How will you proceed? Tell me.
Sir,
What will you do?
dependent vectors.
Dependent vectors.
Dependent vectors.
How do you know
Sir,
this?
dependent.
How do you know this?
Sir, if you V1 plus A2 V2 equal to 0.
What?
Sir, V2 equal to -2 V1.
Without, sir, they have non-zero scalars.
That's why they are linearly dependent. No.
No, sir, V2 equal to -2 V1.
How? Now you are saying that V2 equals to, tell me
Yes,
once
sir.
again. Tell me once again. V2 equals to
-2
-2
V1.
into V1.
-2 into V1. Now, how do you, what is the rule? Now, since this is a very easy example, that's why you can easily check it. But what is the rule? By how can you solve it? How can you find it out? What will you
Sir,
do?
A1
You will
V1
choose.
plus A2 V2 equal to 0.
Yes. Now you tell me the set of matrices, set of 2 by 2 matrix, say it is defined on the set of it is defined over the field of real numbers. So M2 cross 2 R is the set of all possible 2 by 2 matrices. and capital S is a subset of M2 cross 2R. Now, if I want to show that whether it is Li or Ld, my job, mathematical way of doing this is to select two elements, A1 and A2 from R, first of all, and then I will write it as a linear combination. I will multiply the first vector by this. I will multiply the first vector by the first scalar, and I will multiply the second vector by the second scalar. And I will equate it to 0. Now, what is the 0 vector of M2 cross 2R?
0, 0, 0, 0.
Yeah, so 0 matrix is the 0 vector. Remember, in the previous case, the 0 vector was the coordinate or the origin 0, 0. Here, the 0 vector is changing because the vector space is changing. Now, if you solve it, how will you? What will you do? You will write these terms. Is a very easy solution. You are going to do this kind of thing over here. And then after the matrix addition, you will write A1 is equal to, from here you can write A1 minus 2A2 is equal to 0. A1 minus 2A2 is the first element, minus 3A1 plus 6A2 is the second one, minus 2A1 plus 4A2 is the third one, 4A1 minus 8A2 is the last one. So we have got our matrix this, which is equated to 0, 0. And from this, we can get 4 equations. One is A1 minus 2A2, which is equal to 0. Another is minus 3A1 plus 6A2, which is equal to 0. Another is minus 2A1 plus 4A2, which is equal to 0. Another is 4A1 minus 8A2 is equal to 0. And from there, I am getting A1 equal to 2A2. Here I am getting A1 equals to 2A2. Here I am getting
A1 equal to 2A2.
Same thing. The last one is also A1 equal to 2A2. So from each of these cases, I'm getting A1 equals to 2A2. So what we are seeing that A1 equal to this is one way by looking into this, the linearly dependentness. This is another way of looking into the linearly dependentness. Our job is to check. We could have said these two vectors v1 and v2 are linearly independent if the scalars are individually 0, but here the scalars are not coming as individually not coming as 0. Rather, we are getting this result. One is dependent on the other. So scalar is one is dependent on the other. They are not 0, but their linear combination is 0. The scalars are not individually 0, but their linear combination is 0, and therefore these two vectors are LD vectors. Now, same thing is happening in the previous page. In this case, the vector, if I write x and minus x, these two vectors, x is a positive vector, minus x is a negative vector. So if I consider x and minus x, if I ask you that whether x and minus x are linearly dependent or linearly independent, you will immediately say that they are linearly independent. How? Because if I consider a scalar 1 and if I consider a scalar minus 1, and if I add them and equate it to 0, we'll find that the scalars are not individually 0, but their linear combination is 0. But here in this two-dimensional coordinate plane, the vectors 1, 0 and 0, 1, when we choose any arbitrary scalar, A1, A2, this can be positive, this can be negative, anything. What is the nature of the scalar is not important. If I choose any scalar and if I take the linear combination like this, and if I equate it to 0, and if I solve the equation, we find that the only possibility is that this linear equation will be 0 vector or 0 if and only if the scalars are individually 0, otherwise no other possibility is available. And therefore, 1, 0 and 0, 1 are totally linearly independent vectors. Geometrically, one is situated on the x-axis and another is situated on the y-axis. So they are linearly independent. Have you understood?
Yes, sir.
Now the boys, though, those who are speaking, I want to hear from them.
Yes, sir. Understood.
Understood. Okay.
Yes, sir. Understood.
Yes. No doubt in mind? No
sir.
doubt?
No, sir. No,
Okay.
sir.
No, sir.
Okay, okay. During further discussion, I will check whether you have any doubt or not. Anyways, I was talking about, so my observation one was any vector of R2 was where we were able to express any vector of R2 as linear combination of the vectors, or rather distinct vectors 1 0 and 0 1, 1 0 and 0 1. This was our observation one, so that any two-dimensional coordinate can be written as x into 1 0 plus y into 0 1. X and y, the nature of x and y is not important. Observation 2 that we have made over here is that the set in which these vectors 1 0 and 0 1 were residing, this set is a linearly independent set. This set is a linearly independent set because the vectors present inside the set are linearly independent. So these are the two important observations that we have made. Now I am going to give you the third definition. The third definition goes like this. Remember these observations. These are very important. And this particular discussion is also very important. The third definition that I'm going to give you is as follows. A subset capital S of a vector space V generates, or there is another term which we often use, we call it spans V if span of capital S is equal to, the span of capital S is equal to V. The span of capital S is equal to V. If it is so, then we call this particular subset a spanning set of capital V. That means, it means that any vector of V, any vector of the vector space can be generated by the elements of the set capital S. Spanning set, span S means, span S is equal to V means any vector of the vector space V can be generated by the elements of the set capital S, and which is quite obvious. In my example, my V is R2. Now, if I give you a point, like say, for example, if I give you minus 100, 100, this is a very arbitrary point. Okay, so minus 100, 100. Can I represent minus 100, 100 by the elements of capital S? Can I represent it by the element of capital S?
Yes, sir.
Yes,
Yes, sir.
because I can write it as minus 100 into 1 0 and plus 100 into 0 1. You choose any number instead in place of these two, any number of your choice. All the numbers you know are actually, since you are choosing the ordered pair, all the numbers will lie on the two-dimensional plane, and every number can be generated. Every number can be generated by the elements of the set capital S, where capital S is a finite set with distinct vectors 1 0 and 0 1. And therefore, this set that I have considered here is actually the spanning set of R2, because R2 is my vector space over here. So my observation 3 is that capital S spans R2. Understood? Students, understood?
Yes, sir.
Boys?
Yes, sir.
Yeah.
Yes, sir.
Now, if you have understood this particular point, these three particular important points, then I'm going to give you the ultimate definition of today's class. If the bolo.
Sir,
Hmm.
we use always 1,01 and 0,1 in the S, or we can use 2, 3, or any components like that, sir.
Depends on the vector space. Depends on the vector space. So for example, suppose, let me write it in another page. Think of matrix 2 cross 2R. Try to give me, you know that this is a set where this particular set contains any 2 by 2 square matrices of the form this, where A, B, C, D are real numbers. A, B, C, D are real numbers. Now, if you try to find out a kind of set like one which contained 1, 0 and 0, 1 for R2, can you tell me what sort of elements will be there in this particular set, capital S? Let us call it as S1. What sort of elements will be present over there, which can generate every element of this set of matrices? Can you tell me? Will it be 1001? Can 1001 generate ABCD?
Sir, 1111.
1111. 1111.
No, sir.
No,
No, sir.
think. This is the task. What sort of elements will be there, which are not only elements which are linearly independent, they must be linearly independent also, but they can generate every element of M2 cross 2R. Give a little thought, you can find it by yourself. You were asking me, one of the students were asking me that 1001 will always consider 1001 in S. Now, first of all, tell me, can 1001 generate matrix?
No, sir.
Okay. If I consider
No, sir.
1, 2, 3, can it generate a matrix?
No, sir.
A matrix
sir.
can generate a matrix. What sort
Yes,
of
sir.
matrix will be present over here? Now, if I choose like this is the first element, this is the second element, this is the third element, and this is the fourth element. This is your task. Show that right now you can avoid, after class you try, show that it is an Li set. And you see that ABCD, this matrix can be written as A into 1, 0, 0, 0 plus B into 0, 0, 1, 0, 0 plus C into 0, 0, 1, 0 plus D into 0, 0, 0, 1. Am I right?
Yes,
Yes,
sir.
sir.
If I choose a polynomial, set of polynomials, a vector space of polynomials, then we have to consider the this kind of elements in S in a different way. We will discuss polynomials later on, but let me first make you understand the main topic that I was actually trying to establish in this particular class. So as you are asking me whether it is always 1, 0 and 0, 1, no, it depends upon the vector space, what sort of elements you will put inside capital S. Since I started with R2 space, it is a very simple to consider. So therefore I was discussing throughout the class, I was discussing about 1, 0 and 0, 1 because it is easy to realize, because you have done lots of coordinate geometry in your school days. Again, another thing that I'm again asking, another example, suppose I'm instead of R2, if I consider say R3. It's a three-dimensional coordinate system. What will be the what kind of elements will be present in say S2? Tell me.
1 0 0
Yes.
1 0 0 0 1 0 0 0
0
1.
1 0 1.
Yes, now you have got it. Now you have got it. So it depends what vector space you are actually considering. That depends on this. Now let me come to the definition that I was trying to establish in my today's class. So we have got, again I am saying, we have got three important observations. Observation 1, that any vector of R2 can be expressed as linear combination of some finite number of elements. These finite number of elements are linearly independent, and in the set in which they belong is also linearly independent, and the set actually spans R2 because every element of R2 can be generated by the elements present in capital S. Keeping this in mind, I am going to give you the third definition of today's class. The definition goes like this: a basis. Let us denote this basis by beta for a vector space. For a vector space, V is a linearly independent subset, is a linearly independent subset of V that generates P. If beta is a basis for V, we also say that the vectors of beta form a basis for V. Now, what is important in this particular case? What is important in this particular case? That if a particular set beta to be a basis, then it must satisfy two properties. One property is that the set beta must be linearly independent. You already know that what is the meaning of this, and that every vector of V can be generated by the elements of betas. That means beta is Li. This is the first criteria, and number two criteria is
Beta
span,
spam.
not beta span. Span of beta must be equal to the vector space. Span of beta must be equal to vector space. If I keep this definition in mind, then we can immediately say that capital S 1 0 0 1 is a basis of R2. S1 1 0 0 0 1 0 0 0 1 is a basis of R3. S2 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1 is a basis of M2 cross 2R, and so on and so on. We can find out many bases, and the number of elements present, the number of elements present in the basis beta is called what we term as dimension of the vector space, dimension of the vector space under consideration. The dimension of the vector space under consideration. We always like to talk about dimensions. Okay, 3 dimension, 4 dimension, 5 dimension, n dimension. We try to think like that. Okay, we always think of kind of physics about these dimensions, but dimension is a mathematical term whose definition has been established over here. Since S2 spans R2 and it's Li and it is a basis of R2, therefore we call R2 as a 2-dimensional space, 2D space. Since S1 is the basis of R3, we call it as a 3-dimensional space. These are the meanings, actual meanings of dimensions that has been introduced in this particular class. Okay, so when we talk about 11 dimension, that means there is a kind of S which is a basis and which contains 11 elements inside it, which are linearly independent, and it spans the corresponding vector space. Here in this particular case, the dimension of M2 cross 2R, this is equal to 4. Because here 4 elements are present. 4 elements are present. Understood?
Yes, sir.
Yes, sir.
So this is the meaning of dimension. Now remember, it's a remember it is a convention. It is a convention which we in mathematics we always kind of make some conventions. Because in some later chapters, using these conventions, we are actually these conventions become helpful for us to solve different other problems. Let's go back. Let's move back a few pages to some previous pages where let's move back to some few pages and let's come to page number 15. And in section 1.2. If you have probably seen that in section 1.2 exercise, there was an exercise which is exercise number 11 I'm talking about, which actually talks about this particular set. That means a single ton set consists of only one vector, that is 0 vector in it. This vector space, this V is a kind of vector space. It can be shown. Probably you have tried it out. So singleton 0 vector. If you consider a set which contains only the 0 vector, then you can easily show the 8 properties to be that are being satisfied. This vector space has also a basis. This vector space has also a basis, and the convention is that we term this phi. Phi is null set. Phi is actually, by convention, phi is considered to be the spanning set for the vector space 0. And consequently, the dimension of this vector space 0 vector space is equal to 0 because phi has no element in it. It is a convention. You have to remember this. It's a convention. Now, if you are, well aware of contrapositive arguments, then you can, I'm not talking about this right now, but if you are well aware of this contrapositive argument, you can always try to prove that the span phi is indeed 0, because if span phi is not equal to 0, if phi doesn't span 0, then some thing will happen which will lead you to some sort of absurdity, and this, by making these arguments, you can try to check whether it is indeed it can indeed be considered or not. But for the time being, I'm not going into the details of that. So remember,
So this is linearly dependent.
Which one?
So this, because a scalar can be anything.
No, 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 no. Phi is always linearly independent set. I will ask all of you, phi is linearly independent. Remember, since phi is linearly independent, span phi equal to 0. So dimension of this vector space, and 0 is a vector space. I'm in place of 0, I can let me put a bar over here, because each time I put 0, that means it as if it I'm considering number 0, but I'm not considering number 0. I'm considering a vector 0. So for example, if I talk about R2, then if I consider this vector, this particular set 0, 0 only, then we can show that it is a vector space. This set is a vector space. If I consider the matrix, then if I contain in a set only this element, then we can show that this particular set is a vector space. That means these are the special cases. In general, if we consider any 0 vector inside a set, and if the set is a singleton set, we can always show, and it is defined in example 18 of section 1.2, that it is a vector space. Now, every vector space needs to have some sort of spanning set. So it's conventionally, we can consider that phi is the spanning set of the 0 vector space. And not only this, phi is linearly independent also. How can you show this? Because for linearly independent, that is a home task for you. That is a home task for you. If you try to think of the proof that phi is subset of any set, and how will you prove this particular thing? Then try to apply the definition of linearly independentness over here. Linearly independentness over here in case of phi, and show that it is indeed linearly independent. You can try it out in the following manner also. If possible, let phi is linearly dependent set, and then what will happen? If phi is linearly dependent set, then what will happen? Now proceed with your argument, reach to some sort of absurdity, and you will, by this contrapositive argument, you will find you are able to show that phi is linearly independent set. Now span of phi is equal to the 0
But
vector
sir,
space.
the scalar with which we multiply this set can be anything.
Yeah, anything, any scalar, any scalar. There is no restriction on the scalar. Now you just try. I'm not going to, if you are not able to do, you write me in the WhatsApp, and I'm going to give you a hint, or I'm going to give you a solution later on. Now I'm saying that this actually the vector space, this 0 vector space is defined on, remember this 0 vector space is defined over any field capital F. It is defined over any field capital F. It's there is no such restriction that it should be a real set of real numbers or complex numbers. Any field you can choose. So there is no such restriction on the scalar. Only restriction is that it has to be chosen from a field. You cannot consider the scalar to be an element of a set which is not a field, because ultimately we are
Do we
dealing with.
need to reconnect?
You have to.
Do we have to rejoin?
How much
The
time
class
is left?
is going to end.
Yeah, class is
sir,
going
1
to end.
minute.
My class is still how much time is left for the class?
20 minutes.
20 minutes. Then you rejoin. Then
Okay,
after
sir.
the class ends, you rejoin once again. Okay, I'm stopping here right now. Let's discuss in the next class some few more points, and then we'll end the class for today.